Optimization in terms of calculus. To optimize in calculus means to maximize or minimize some aspect of a function. For example, we may want to maximize the area of a certain shape, or we may want to minimize the cost of a certain operation. The way this is done is by using the derivative equation, which, when set equal to 0, yields the maximum and a minimum value, or values, of a function. Because if we have our function which describes our operation, when we differentiate at these points where there are minimums and maximums, the slope is 0. That means the tangent line at these points is 0. So the slope of the tangent line is the derivative. So setting the derivative equal to 0 gets us these minimum and maximum x values, the locations at which these occur. This explanation is too simplified, but the concept of optimization is one that is best learned through examples. So this is by no means a complete definition, but it's best to use examples to learn this concept anyways. So we'll get to that now. An example. Find the maximum area of a rectangle with perimeter of 149 centimeters. First thing we want to do is write down some of the formulas that we will need to use when dealing with this, because what we're essentially doing is manipulating formulas in order to find the maximum area. So let's write down some formulas. One formula we know is area. We'll call that capital A. This, for a rectangle, area equals length times width, L times W. Formula for perimeter. Perimeter equals 2 times the length plus 2 times the width. But what do we also know? We also know perimeter is equal to 149 centimeters. We don't need the units when dealing with the math, but in the end, we'll need to recognize what the units were. So first things first, we can set these two equal by eliminating p, so 2L plus 2W equals 149. At this point, since this is the second and only other formula we have at this point, we need to eliminate one of the two variables in our area function. Area right now is a function of two values, length and width. However, we can't differentiate area. We cannot optimize or find the maximum of the area if there's two different variables, because we can't differentiate that. So we need to get area in terms of one variable. So let's arbitrarily choose L at length. So solve for L. 2L equals 149 minus 2W. So L is equal to 149 minus 2W, all divided by 2. Now we can put L into our area formula. Area equals, we know L in terms of W is 149 minus 2W divided by 2. This quantity represents L. Multiply this by W. Simplifying this, we get area is equal to 149W minus 2W squared, this quantity times 1/2. So just bringing the denominator out as a coefficient of the entire function, area. Now, we'll move up here and solve for A prime. A prime, we just have a coefficient, so that's fine. We get 149 minus 4W. As we saw earlier in the definition stage, to optimize the derivative in order to find the maximum and minimum, in this case the maximum, A prime needs to equal 0, so we can find, in this case, the W, the width, at which there is a maximum area, given the parameters of the limited perimeter we have to work with. So 0 is equal to 1/2 times 149 minus 4w. 0 equals 149 divided by 2 minus 2w. Moving 2w over to the other side, we have 2w equals 149 divided by 2. So 4w equals 149. W equals 149 fourths, which is equal to 37.25. So we solved for width. Having solved for width, we can solve for length, because we have a formula up here where we have perimeter, which is known, and width, which is now known, giving us only an unknown of length. But now we can solve for this unknown because we have 2 out of the 3 variables. So 149 is equal to 2L plus 2W. All we need to do is plug in W. So 149 minus 2 times W, which is 37.25, is equal to 2L. On the left, that gives us 74.5, which is equal to 2L, giving us an L value of 37.25. Now this is interesting because it's the same as W. So what you'll find with a problem like this is that when you optimize area of a rectangle, you get a square. And this is always the case, because the square is the most optimized, in terms of area, the most optimized shape of rectangular form. So to finish the problem, we will write in this little space here that dimensions that maximize the area of the rectangle are length of 37.25, and let's remember our units of centimeters, and width of 37.25 centimeters. A rectangle has its base on the x-axis and its upper 2 vertices on the parabola y equals 12 minus x squared. What is the largest area the rectangle can have, and what are its dimensions? So again, we're finding the largest area, in other words, maximizing area of, again, a rectangle, but we have some limitations here. So it's inscribed in the parabola y equals 12 minus x squared. First things first, we need to graph this parabola. So we'll do the best we can for graphing. And a more helpful way of looking at this function, y equals 12 minus x squared, is y is equal to negative x squared plus 12. So we know this is a vertical translation, and we know that because of the negative, we're looking at an upside-down parabola. So we know it's up to y equals 12. So up here at 12, and it's upside down, almost like that, if we could draw. So now we have a rectangle inside. Let's draw this rectangle. So there's our rectangle. And what do we know about this already? So we know that the point where the rectangle and the parabola connect has the coordinates xy. That is, with every point on the xy plane. Every single point has the coordinates xy as a generalized form. So what we can tell from this already is that this height of this side of the rectangle is equal to y. It's this distance above y equals 0. We also know that this distance is equal to x. It is this far to the right of x equals 0. So we know that this entire base is equal to 2x. So now that we have the visualization, we didn't need to do this in the previous one because we all know what a rectangle looks like. But this is slightly more complex in that we have the limitations of this parabola, and we're not given anything specific with this rectangle. We're given implicitly related information in the form of a parabola. So continuing, now we'll begin like the other problem in that we'll write down our formulas. So A is equal to L times W, length times width. That is the case with all rectangles. But what else do we know? Again, we can't leave area a function of two different variables, length and width. We can't do anything with two different variables. So we will generalize the width as, well, the width, and we'll call the length what is the height of the rectangle. So length is equal to y, and we know that y is equal to 12 minus x squared. Now w, we know, is 2x, twice the distance of one side to the base of the rectangle. So area equals 12 minus x squared times 2x, simplifying to 24x minus 2x cubed. Again, differentiating a to optimize it, finding its maximum. A prime equals 24 minus 6x squared. We can simplify this further. A prime equals 6 times 4 minus x squared. A prime equals 0. 0 equals 6 times 4 minus x squared. We know that x equals plus or minus 2, but we know that x cannot equal negative 2 because we're looking at this in terms of distances. So our x is equal to 2, y is equal to 12 minus x squared, y is equal to 12 minus, plugging in the 2 that we found for our x, y is equal to 8. Area equals length times width. Our length, being our y, is 8. Our width, being 2x, is 4. So area is 32 units squared. So to finalize our answer, we say the largest area the rectangle can have is 32 units squared, with dimensions length equals 8 and width equals 4. Now, to clarify an earlier point in saying that x does not equal negative 2, one of the x values does equal negative 2. However, because we're looking at lengths, we take the absolute value of this, and because x is the same on either side of the axis, we can look at only the positive value because we're looking at strictly lengths, and lengths can only be positive values.